All right, so in this video, we are going to take a look how to determine if a function is one-to-one algebraically, and we are also going to find the inverse if it is one-to-one, and then we're also going to verify graphically. So let's take a look at this first example. We have g of x is equal to x plus 2 quantity cubed. So the way to verify algebraically is, if f of a, right, is equal to f of b, the result is that a has to equal b, right? For a particular set of y values that equal each other, it can only have one x value. So that's basically what this is saying. So if I just plug in my, in this case, the function is g. If I plug in a, right, I'm going to get x plus 2 quantity cubed. F of b, right, in this case, g of b, you're going to get b plus 2 quantity cubed. And you could FOIL this, okay, but you know what? I'm just going to take the cube root of both sides. All right, the cube root of both sides. The cube root of a cube root is just the argument itself. And quickly you will see that a does equal b. Okay, so I verified algebraically it's one-to-one. And if it is one-to-one, right, we're going to actually find the inverse. So how do you find the inverse? So in the previous video, right, I basically stated that you want to switch, okay, the x and y. So let's switch it. X is equal to y plus 2 quantity cubed. And then the next step is you want to get y by itself. Okay, so how do I get y by itself? You take the cube root of both sides. You're going to get the cube root of x is equal to y plus 2. And then you're going to get the cube root of x, right, minus 2 is equal to y. And then call this your g inverse of x. Okay, so call this your g inverse of x. There is your inverse. And let me just erase this right here. Let's see if I can erase. Okay. So if you were to graph this, verify algebraically, how would I verify graphically? So all I'm going to do is just go to Desmos, right? And then just plot this. Or actually, you don't even need to go to Desmos. You could just recognize that this is your cubic function. And in order for it to be one-to-one, right, it has to pass the horizontal line test, right? So this is your cubic function shifted 2 units to the left. And it's going to look something like this. All right, clearly, right, it's going to pass the HLT. Therefore, one-to-one. Okay, so algebraically, you set two y values equal. Make sure that the x values that you plug in have to equal. How do you actually find the inverse? Once you know it's one-to-one because the inverse exists, you switch the x and y, get y by itself, and then call it whatever your function name is, but call it the g inverse, f inverse, or whatnot. Okay, and then graphically, right, you can see that it's clearly going to pass the HLT. It's only going to intersect one time. All right, so I had the previous example over here, part B, that erased. I had f of x is equal to x squared minus x to the fourth. Okay, so this example, I will caution you that the algebra is relatively tricky, but I'm confident that you guys can follow along. Okay, so assuming that f of a is equal to f of b, right, I need to show that a is equal to b. If a does not equal to b, it's not one-to-one. If it's not one-to-one, it does not have an inverse. All right, so f of a, right, is just a squared minus a to the fourth. F of b is b squared minus b to the fourth. Okay, somehow I need to show that a equals b. If it doesn't, then we know it's not one-to-one. All right, so what you should do right here is just move all the terms over to one side. And that's what I'm going to do. Okay, minus b squared positive b to the fourth is equal to 0. Now, when you see a bunch of terms like this, right, what you want to do is do a little bit of factoring, okay? And you want to group specific terms together. And the terms I'm going to group together are a squared minus b squared okay? And then over here, I have negative a to the fourth plus b to the fourth. So what I did was rearrange some terms. And now what I'm going to do is I'm going to keep my a squared minus b squared. You already know that's difference of two squares, right? But between these two terms, what I'm going to factor out, right? What I'm going to factor out is a negative 1. Okay, so I'm going to factor out a negative 1 between these two terms. And I'm going to have a to the fourth minus b to the fourth. And now, hopefully you can see that this is just a pattern of difference of two squares, right? This is a squared squared minus b squared squared, right? That's this pattern right here. So if I factor this, this is a squared plus b squared times a squared minus b squared, right? That's difference of two squares. And over here, right, I already have my a squared minus b squared. So factoring by grouping, this term and this term are common. I'm going to factor it out. And what's left is a 1 minus parentheses a squared plus b squared. Okay, so I know some of you are probably looking at this. You're like, what the heck just happened? This is just factoring. Okay, so factoring difference of two squares, factoring with a quartic term. Okay, so where does that leave us? Well, where that leaves us now, right, is you could use the zero product rule. You have a squared minus b squared is equal to 0, or 1 minus parentheses a squared plus b squared is equal to 0. So over here, right, you have a plus b times a minus b is equal to 0. And when you set these guys equal to 0, you'll notice for this factor, right, or this linear equation, you have a is equal to b. That's good. But a clearly equals negative b over here, right? That's not good. Once you arrive at a contradiction, you can stop. You could also see over here, right, that if I were to move this over, right, if I get a squared by itself, a squared is equal to 1 minus b squared, and you take the square root of both sides, right? A is going to equal plus or minus. This is no good. So you could say, therefore, not 1 to 1, since a does not equal b, right? Over here, a does not equal b. Over here, a does not equal b, okay? But the algebra in this one, right, is really, really complicated, but it's good practice for you to